that last video, we saw that to have a buffered solution, we have to have amounts of the acid as well as its conjugate base present. But we didn't really see how that resists a change in pH. So here to demonstrate that, I've got a three-part problem that we're going to go through. And we're going to take it one part at a time. And this is going to demonstrate to us how buffers resist a change in pH. So in this first one, a buffered solution contains 0.5 molar acetic acid and 0.5 molar sodium acetate. Calculate the pH. And so I'm just going to go straight into that on this other page right here where I've got lots of open room. So number one, so we need to set up the rice table, right? So that's acetic acid, CH3COOH, okay? And that makes the acetate ion, CH3COO minus, as well as H plus, okay? And if we go through here and set up our rice table, we should now at this point be pretty good and practiced with this. I still can't seem to draw these lines straight at all, but that's okay. So 0.5 molar acetic acid, 0.5 molar sodium acetate. So the way that we do that, right, is we say that we've got 0.5 molar of this, 0.5 molar of this, and we say that we're going to have 0 of that stuff initially, okay? And now, of course, because that's 0, that's got to be plus x, which means this has to be plus x, which means this needs to be minus x. And if I go through filling that out, 0.5 minus x, 0.50 plus x, and now just x. And we were given the Ka is quite small, 1.8 times 10 minus 5. And so given that the Ka is small in comparison to my initial concentration, we can be confident that the 5% rule is going to work. So 0.5 and 0.5 and still x. So we're saying that the value of x is small compared to that 0.5. So then now when I go to set this up, okay, I'm going to do this as the equilibrium expression. 1.8 times 10 minus 5 equals, and that's going to be H plus times acetate, which is just simply x times 0.5 divided by acetic acid, which is 0.5. So you can see here, this one is really straightforward. The 0.5 and the 0.5 cancel. X is 1.8 times 10 minus 5, which we know is the H plus concentration. So the pH equals the negative log of 1.8 times 10 to the minus 5, which equals E minus 5, and then log, and of course times negative. So that would be 4.74. So let's write that down. So the pH for this problem was 4.74. Okay. So now what we're going to do is calculate the change in pH that occurs when 0.01 moles of solid sodium hydroxide is added to 1 liter of the buffered solution above. So that means what we have here is 1 liter of 0.5 molar acetic acid mixed with 0.5 molar sodium acetate, and we're going to add 0.01 moles of solid sodium hydroxide. So we expect that the pH should go up because we're adding base to this acid buffer. And even if it wasn't a buffer, we're still adding base to an acid. So the pH should increase, right? We should expect to see that. So let's go for it. And then now to do this, I'm going to introduce a new type of calculation. I like to call this a before and after. So we'll set up our reaction here, CH3COOH, but now we have to consider that it's the hydroxide, right? We don't care about the sodium. We know it's a spectator, but it's this hydroxide that's going to react, and we have to remember what it's going to react with. So either the acetic acid or the sodium acetate. Well, it has to be the acetic acid, right? Because hydroxide is a base, acetic acid is an acid, so the acid and base has to react. So now I'm going to set this up as CH3COOH, acetic acid, plus OH minus. And as it turns out, this is a full reaction. This is not an equilibrium reaction. That strong base will react with the acetic acid and go to completion. Okay, and so what that leaves behind now is CH3COO minus plus H2O. Okay, and so now what we're going to need to do here, so we'll first set up our before column. Okay, and in this before column, I want to calculate all of the number of moles of my species in question. Okay, so I don't want the molarity, excuse me, I want the number of moles. And so we were told that it's 1.0 liter times 0.5 molar, which is the same as 0.5 moles per liter. So we can see, I used pretty straightforward numbers for this example here. So we recognize that we've got 0.50 mole of acetic acid. We would also have the same amount of acetate, because remember we had 0.5 molar solution of acetate. And then my hydroxide was 0.01 mole. Okay, 0.01 mole. And so now what happens with this thing? Well, because this is a full reaction, all of these amounts are going to react. So now I'm going to write here in the after row, we know what's going to happen here is all of the hydroxide is going to react because this is a limiting reagent situation, right? The species that's present in the lowest abundance will react to completion, and in that case, it's the hydroxide. So if 0.01 mole of hydroxide reacts, then that means 0.01 mole of acetic acid has to also react. But that also means that 0.01 mole of acetate has to be formed, right? So if I consume 0.01 mole of acetic acid, right, negative 0.01, then that means I'm going to produce positive 0.01 mole of acetate. And so now that means after this reaction has gone to completion, we have 0 hydroxide left. We have 0.49 mole of acetic acid left, and we have 0.51 mole of acetate. So now these represent our new equilibrium concentrations, and what we want to do is convert them back into molarity and plug them back into our Rice table. And so now it's tempting to say, well, why didn't we just use the molarity in the first place? Because as you can see, the math would have worked out. I want to caution you against that, because if we're in a situation where we don't have a nice even number like 1.0 liters, then the math is not going to work out. So we do want to take the time to convert our concentrations into absolute number of moles, figure out how much reacts, and then convert them back into molarity concentration. Okay. So now we have our new equilibrium values, which for acetic acid is going to be 0.49 molar. And for acetate, it's going to be 0.51 molar. And instead of setting up a brand new Rice table right here, you can see, I can just go straight for how I set it up in the expression, which is going to be now 1.8 times 10 minus 5. And so remember, it's not this. We're not making a Rice table out of this table number 2. It's this reaction. And so now my new acetic acid concentration is 0.49 molar, which I put on the bottom, right? And my H plus concentration is still X, because that's what we're solving for. And then now, as you can see, my new acetate concentration is 0.51 that I'm going to put right there. Okay. So now when I calculate that here, X is going to equal something just slightly different than what it did before. So 0.51 divided by 0.49, okay? So that all equals 1.04, and then I can divide that over to the other side, right? So let's say 1.8 e to the negative 5, and now that's divided by that 1.04 number, and now I get x to equal 1.7 times 10 to the minus 5. And then, of course, the pH is the negative log of that number. Okay, and we can, since it's on my calculator here, I can just push log. And there we go. And remember, the negative sign is going to go away. And so that is 4.76. So what does all that mean? Well, okay, look. We calculated the pH of this solution. Originally, it was 4.74. And now, upon adding 0.01 moles of solid sodium hydroxide to 1 liter of that solution, the pH barely changes, 4.76. So that is a very, very small change in pH. And we can see here the buffering ability of this solution. And then finally, on this third calculation, compare this to adding 0.01 mole of solid NaOH to 1 liter of pure water. Well, we know the pH of pure water is 7.00, right? And so now if I add 0.01 mole of solid hydroxide to 1 liter of that, that's going to be 0.01 mole of hydroxide in 1.0 liter, which is 0.010 molar. And of course, if I take the negative log of that, that gives me the POH. So let's do that. So the POH is the negative log of 0.010, which hopefully you can see that in your head, that's going to be 2.00. But just to confirm, right, if I say 0.01 and then do the log, oops, what happened? Let's see. 0.01 and then take the log of that equals, why aren't you doing this for me? Log of 0.01 equals, oh, come on, calculator. Well, you guys are going to have to trust me on this one. That is a POH of 2.00, which means the pH is 12.00. So again, in thinking about how this problem goes, okay, if I have the solution, pH 4.74, I add hydroxide, and it barely changes. It becomes 4.76. But now, if I compare this, if I was adding that same amount of hydroxide to just ordinary water without any buffering capacity in that water, right? So you can see now that skyrockets to a pH of 12.0 after the addition of hydroxide. So again, you can see here when we have this conjugate acid, weak acid and its conjugate base, that makes a buffered solution, and it does a really good job of resisting a change in pH when something is added to it to perturb its equilibrium.